In this video, I discuss two problems with Excel's solver add-in that when you solve a non-linear optimization problem, sometimes the sensitivity report does not report the Lagrange multipliers. There is a way to fool Excel into producing Lagrange multipliers, but you have to set up the constraints in a very particular way. And if you don't, those Lagrange multipliers can be the wrong value. In fact, they'll be the opposite sign of the actual Lagrange multipliers. So what I'll do is I'm going to show you the following. So given that the sensitivity report doesn't always produce Lagrange multipliers, and even if it does, it produces a wrong sign, we're going to show you how to fix the problem. So let's take a problem where you have to maximize y subject to this constraint and that constraint. If your constraints are on x, the decision variable, you're not going to get the Lagrange multipliers. So to get the Lagrange multipliers and get the right sign, what you then have to do is, for this constraint, you must make a new cell that, let's call it, let's reverse the inequality first. So it'll be minus x, let's make it minus c1. And this pink minus x is equal to minus 1 times the decision variable. So it's not minus x, the decision variable, is actually equal to minus 1, the x decision variable. Since this is already is a less than equal form, you leave it as it is, but you still have to invent or make up a new x that's equal to the actual decision variable. And then finally, the sensitivity report doesn't always produce sensible looking labels for the constraints. Now I'll show you how to do that. Alrighty, so sorry, this mouse is a bit, okay, here we go. So let's consider the following problem. You want to maximize this function of y, making sure that you respect these two constraints. A, B, C are positive, and C1, C2 are in the domain, and of course C2 has to be bigger than C1. So you're looking at a picture that looks something like this, and it could be that I'm just making something up. C1 could be here, C2 could be there. So X has to fall somewhere in between right here. So first I'll demonstrate why, if you use the X decision variable in the constraints, you will not get the Lagrange multipliers. Next, I'll show you how to make up a new X and then hope that that way you produce Lagrange multipliers. Well, you'll see that it will. So this is a new X that's equal to the decision variables and so forth, but you'll get the Lagrange multipliers, but the wrong sign. Therefore, to get the right Lagrange multipliers, you must express all inequality constraints in less than or equal to form. So this constraint will become that constraint, but once again, minus pink x is equal to minus the actual x. And then this constraint is already less than or equal to, but it must be produced in a separate line where this red x is equal to the actual x. And finally, I need to remind you that if you want to know the change in y star due to change in parameters, you must use the envelope theorem. To get the full benefit of this, I think we should solve this by hand so we know that in fact we have the right Lagrange multipliers. This is a good exercise just again in reviewing optimization, not only because you need it for the winter semester, but also because you need it for the final exam. So let's begin. You have this problem right here, and remember that A, B, C are positive. So you can see what I've done here is A is equal to 1, B is equal to 10, and C is equal to 5. And I'm going to consider various cases. So you will notice that I consider the first case, which is C1 is 2 and C2 is 4. That's your case B. In case C, I make C1 6 and C2 10. And in case D, I make C1 0 and C2 10. So basically, X can lie anywhere between 0 and 10. All right, let's start. So our problem is maximize y, which is a function of x. That's equal to, if it's okay with you, I'll do it in terms of a, b's, and c's, and then fill in the numbers later. It'll just be a more powerful exercise. Minus c, such that x is bigger than c1 and x is less than c2. Now, you remember that we have been saying all along that all constraints must be less or equal to. So we'll do this and we'll do this. Now, you will use this form of constraints in Excel, where remember that these x's must be a new cell equal to the actual x. But when you do it by hand, you need to make sure that the only number on the right side is the number 0. So there we go. And now we're good to go. You want to maximize, choose x, lambda 1, lambda 2, the Lagrange equation. The first term is always your y equation, always followed by a lambda sign, lambda minus sign, and then lambda 1. Then you put the left hand side of that constraint, so that'll be equal to minus x plus c1, minus sign, lambda 2, left hand side of that constraint. So that'll be x minus c2. Differentiate the Lagrange equation with respect to x. It'll be minus 2ax plus b plus lambda 1 minus lambda 2 is equal to 0. And now you have Kuhn-Tucker conditions. Lambda 1 must be bigger than or equal to 0. X must be bigger than or equal to c1. And by Kuhn-Tucker conditions, this entire expression is going to go to 0. So you say lambda 1 minus x plus c1 is equal to 0. And of course, the second constraint, lambda 2 must be equal to 0. X must be less than or equal to c2. And then by Kuhn-Tucker conditions, this entire expression must be 0. My recommendation, just out of years of experience, is now you have to split in cases. I would start with this one right here. So if you look at this one right here, it implies one of two things. And I would put the x, so two things have to be true, right? Either two things must be true. Either lambda is 0 or x is equal to c2. Put the x is equal to c2 here. You'll see why I do this. And put the other possibility that lambda 2 is equal to 0 here. If x is equal to c2, you will have to ultimately check whether lambda 2 is bigger than or equal to 0. And if lambda 2 is 0, you will have to check whether x is less than or equal to c2. Now consider the first constraint. This one right here. That gives you two possibilities here and the same two possibilities over here. Try to put the lambda zeros on the right and put everything else on the left. So for example, if you're talking about the x's, either x is equal to c1, x is equal to c1, or lambda 1 is equal to 0, or lambda 1 is equal to 0. If x is equal to c1, then you must check whether lambda 1 is bigger or equal to 0. And if lambda 1 is 0, you must check if x is bigger than c1. Same thing here. Lambda 1 is bigger than 0. Is that true? And is x bigger than or equal to c1? If I now take this to the next slide, I can summarize this. And what will happen is something like this. You will notice that I get 4 cases. I'll get case A, B, C, and D. Let's talk about x and c1 first. Under case A, the leftmost branch, you have x is equal to c1. What about c2? Well, x is also required to be equal to c2. And we have to check whether lambda 1 is bigger than or equal to 0, lambda 2 is bigger than or equal to 0. Under case B, we are required to check whether x is bigger than c1. We know that x is equal to c2. We know lambda 1 is 0. And we have to check whether lambda 2 is bigger than or equal to 0. Under case C, we know that x is equal to c1. But we have to check whether x is less than or equal to c2. We also have to check whether lambda 1 is bigger than 0, bigger or equal to 0. And we know that lambda 2 is equal to 0. And finally, under case D, we must check whether x is bigger than c1, x is less than c2, and we know for a fact that lambda 1 and lambda 2 are equal to 0. Notice this is impossible because you're asking x to be equal to c1 and x equal to c2, but you remember that c2 must be equal to c1. So A is never the solution. So you can see the wisdom in putting, when you set this tree up, it's always better to put the x conditions on the left and the lambda conditions on the right. That way you'll get the familiar, always the same form. B would then be a boundary solution, C would be a boundary solution, D would be an interior solution. Now here we know that x is required to be bigger than c1. Is it? X for sure is c2. Lambda 1 is equal to 0, and lambda 2 is bigger than or equal to 0. To solve this, I bring the first order condition. And if you remember, the first order condition was minus 2ax plus b plus lambda 1 minus lambda 2 is equal to 0. So what can we put in here? We know that x is c2, so that'll become c2. We have b over here, lambda 1 is 0, and now minus lambda 2. And we know that lambda 2 is required to be positive, so isolating lambda 2 gives you, let's see, b minus 2ac2. And we wonder when this is bigger than or equal to 0. It'll be, well, if you turn it around, you'll see that this will be true when, well, I'll do it for you just to make sure we don't make any mistakes. And then this, of course, says c2 must be less than b over 2a. So therefore, when c2 is less than b over 2a, x1 will be equal to c2, which, by the way, is bigger than c1, so that condition is met right there. Lambda 1 will be 0, and lambda 2 will be equal to b minus 2ac2. So what's happening, of course, is, if you remember, for a function that looks like this, the unconstrained solution is b over 2a. So therefore, if c2 is over here, and it doesn't matter where c1 is, I'm just going to make something up, then you know x has to be here. Trying to maximize a function, no wonder the solution is x is equal to c2, and that'll be your y star constraint. Next up, we know x is equal to c1. We want to know whether does that mean it's also less than equal to c2? Well, of course, yes, because c1 is less than c2. So we know that is going to be satisfied. We wonder if lambda 1 is bigger than 0, and we know that lambda 2 is 0. Again, by the first order condition, which was minus 2ax plus b plus lambda 1 minus lambda 2 is equal to 0, we now know that x is equal to c1 plus b. Lambda 1 is supposed to be a number bigger than or equal to 0, but lambda 2 for sure is 0. Therefore, lambda 1 is going to be equal to 2ac1 minus b. We wonder when that's bigger than or equal to 0, and the answer, of course, is when c is bigger than 2a. So what's happening here, of course, is you have the function like this. The unconstrained solution is b over 2a. c1 is bigger than this. So therefore, if you want to maximize the function, you must be at least bigger than or equal to c1. So no wonder the answer is x is equal to c1. Lambda 1 would then be equal to 2a c1 minus b. And then, of course, lambda 2 is equal to 0. And that's your y star constraint. Finally, you wonder, the easiest way to think about this is if neither cases b or c arise, you must be in case d, where x must be bigger than c1. It must also be simultaneously less than c2, and both the lambdas are 0. So again, you see the benefit of setting up the tree in such a way that the right side is always lambdas zeros, because you'll always consistently get the same kind of A, B, C, Ds, where Ds always have the interior solution. Take the first order condition, minus 2x plus b plus lambda 1 minus lambda 2 is equal to 0. Now we know that the lambdas are 0, therefore x must be equal to excuse me, b over 2a. So therefore, one way of writing this down would be, if c1 is less than or equal to b over 2a is less than or equal to c2, then x is going to be equal to b over 2a, and lambda 1 is going to be equal to lambda 2 is equal to 0. And that's your solution right there. Just in passing, we should probably just point out that how to find out that the lambdas are not necessarily a change in y star due to change in parameters. So in this particular problem, you had the Lagrange equation. It was minus ax squared plus bx minus c minus lambda 1 is minus x plus c1 minus lambda 2 into x minus c2. Now, if you remember, at the optimal solution, this of course is your y. So the optimal solution, this will be y constrained, and then the next two terms are going to be 0 by the Kuhn-Tucker conditions. So the value of L star is always equal to the value of y subject to constraints. So if somebody says, what's the change in y star constrained due to a change in a parameter, you should be then looking for the change in L star due to the change in parameter. And for that, you use a good friend, the envelope theorem. The envelope theorem says, go to the original equation, not the L star equation, and differentiate with respect to parameter. So for example, if you want to know how y star changes when c1 changes, you would differentiate the Lagrange equation, or original Lagrange equation, with respect to C1. And you can see when you differentiate with respect to C1, the answer is going to be minus lambda 1. That means the change in L star over the change in C1 is minus 1 lambda 1 star. And since L star is the same as y star constraint, the change in the value of y constraint over the change in C1 will be equal to minus 1 lambda star. And then, of course, the value of this will depend on whether you're in case B, C, or D. Because in case B, minus lambda 1 star is 0. In the case C, minus lambda 1 star would then be equal to, if you just look back at your note, minus 2a C1 minus B. And in the case D, that's equal to 0. And now, what if you want to know ultimately the change in y star due to change in C2? Differentiate the original equation with respect to C2, and the answer is lambda 2. Therefore, the change in L star over the change in C2 is lambda 2 star, which means the change in y star constrained over the change in C2 is going to be equal to lambda 2 star. And again, it depends on which case you're in, B, C, or D. Because in case B, lambda 2 star was equal to B minus 2a C2. In case C, lambda 2 star was equal to 0. And in case D, lambda 2 star is equal to 0. So this gives you the change in y stars due to change in parameters. I'm now going to do this problem in Excel. So let's hang up and then I'll come back.